Everybody beard up? Can everybody read this?
No.
No? That probably didn't do anything. Huh? Unfortunately, this is going to be as large as it's going to be able to go because I'm actually giving the actual slides are in Vim, so there are specifically for exactly this many lines, so it's not going to get any bigger. But luckily, they're available on GitHub. If you want to download the slides and run the presentation on your computer, you can. The talk is going to be on 1 hour ML. We're going to write an ML compiler from scratch in an hour. I hope. This is going to be kind of a tight squeeze. So some reading, if you're interested in the subject, this is going to be loosely inspired by Write Yourself a Scheme in 48 Hours. There's an excellent tutorial on writing a scheme interpreter in Haskell. It uses a lot of the same underlying technology that this is going to use. In our compiler, we're going to use Parsec and JMacro. Parsec for parsing, JMacro for our code generation. JMacro is written by Gershom, who's the organizer of the talk tonight. The type system that we're going to be using is roughly a bastardization of the algorithm presented in typing Haskell and Haskell. If you want a much, much more rigorous implementation of what you're going to see tonight, you should take a look at it. The slides are available on GitHub. And if you like what you see, you should check out the language that, this one right here. If you're interested in this topic, you should take a look at forml, which is a language that I wrote that's very similar to this in architecture and purpose. Unfortunately, we're not going to be talking about it tonight, except for this one slide where I'm going to implore you to go take a look at forml on GitHub. This language. So let's get right down to it. Does everybody here know what ML is? Does anybody not know what it is? Unfortunately, I'm not going to be telling you. If you're interested in what ML programming is, you should take a look on Wikipedia. It's very similar to Haskell. So to start with, we're going to need some language extensions. If you're not familiar with what they are, don't worry. We'll be talking about them as we use them. We're going to need a couple of libraries, a couple of control libraries, a couple of data structures, nothing really particularly interesting here. These modules from Parsec, which we're going to be using for parsing, and this one little hanger-on from JMacro, which we're going to be using to do our code generation to JavaScript at the end of the talk. So I'll bet you're all really excited to see what this language looks like. Nobody. All right, cool. So this is going to be a very simple expression language, which this little humble guy right here is a really simple example of an entire program in this language. 2 + 2 = 4. So a couple of things to note about this is we're lifting types and operators directly from JavaScript, which is going to be our target. That means only doubles. So an integer plus a double is another double. As an expression language, every program is going to evaluate down to a single value. This is going to evaluate down to the value true. And basically, all of the syntax for things like strings, numbers, booleans are going to be lifted directly from JavaScript. Our language is going to have a type system. Our type system is not going to involve any annotations. It's going to be entirely inferred. And as an expression language, every program is going to evaluate to a single type. So this obviously doesn't evaluate. We're trying to add a string to a 4 here. This should generate a type error. And a property we're going to talk about later on during the type inference section is it is a property of this type system that every program can determine what's called a principal type for the program, which is to say that there's one most general type, and our algorithm for type inference is going to be guaranteed to find that type. We're going to allow you to introduce symbols into scope in these programs with the let keyword. So here we're going to say let x equal some value, followed by a semicolon, followed by the continuation of the expression. In this case, an expression that uses the symbol that we just introduced. The semicolon is important because I want to keep the parsing very simple, so a program like this is going to be invalid. We're going to have functions in this language. A function looks like this, the keyword fun, a symbol that you're introducing, an arrow, and an expression. Functions can be bound to symbols with the let keyword we saw in the previous slide. And you're going to be able to apply functions via prefix application exactly as you would in Haskell or any other ML derivative. Our language is going to have simple pattern matching. Pattern matching in the style of ML, not exactly like Haskell. Match some expression with, and then a set of cases, one value with a set of patterns. Here we have semicolon separating each individual case, and another second semicolon at the end of the last case to separate the let from the continuation of the expression. We're also going to allow the user to input their own data constructors. This is going to work slightly differently than you might be familiar with. You're actually going to explicitly say what the name of your data constructor is and its type signature. You're not going to be introducing your own types as you would in Haskell. This is a very simple language. We're not doing strictness analysis or anything like that. So while this might seem like a little bit of a bizarre syntax, it's going to make some of the code generation and parsing stuff a little easier later on. One thing to note about this is even though we're writing the entire return type for these data constructors here, and it looks like maybe you could express generalized abstract data types in this syntax. You actually can't, and we're going to be checking for those during the type inference part of the talk. Our type inference algorithm is going to be able to track type polymorphism over our constructors. So in this case, we're introducing these two data constructors, just and none, which are type maybe A. And when we apply match to this construction right here, this should generate an error, because the type variable that's being bound by this application is a num, not a string. If this doesn't mean anything to you, don't worry about it. If it does mean anything to you, this language does not have kind inference. All of our type variables are going to be monotypes. And what that basically means is you're not going to be able to write type signatures like this. F applied to X is not a valid type signature in this language. And of course, our language isn't going to do silly stuff with parsing or assigning to variables that are supposed to be immutable or anything like that. All right, so let's get right down to brass tacks here. What is the architecture of our compiler going to be? Well, it's actually really simple. It's just going to be these four functions right here. Parse, piped into typecheck, piped into generate.js, piped into toText. And if you look at the type of this function right here, string to either error string, then you can get a pretty good idea of exactly what all of these functions do. So parser HML is type string to either error expression. Typecheck, I'm sure you can guess, is an expression to a type error expression. We're just going to be piping these four very simple functions together and pushing the errors down the stack as we go if they happen to happen in any portion. So we're going to need a data structure to represent this language. And this is going to be section 1 here. The data structure is going to be type expression. And these are all of the constructors for the various semantics of our language. A data expression takes some sort of type sim, some sort of type that represents what the data constructor is going to be, and the expression, which is the rest of the body of the program. A let expression, which is very similar. An app expression, which is a function application. So F applied to X, expression. An abstraction expression, which might be a terminology that might be a little unfamiliar to you, but it's just a function. A var expression is just a high-level wrapper that's going to wrap values and symbols in our language. And a match expression, which is going to be a list of tuples that's going to represent all of the individual cases of our matches. Our language is going to have patterns, just two types of patterns, values and constructors. We're going to have these types of values, symbols, literals, and things that start with a capital letter, the data constructors themselves. And we're going to need a data structure to represent our types. If you look at some other treatments of ML or type inference algorithms in general, you're going to see lots of different ways to represent this. I'm trying to minimize this to make it as simple as possible. One of the things that you need to be able to do if you're writing the entire compiler, you're going to need a data structure to represent the actual parse of the text that represents a type, like in a data constructor annotation. You also need a data structure to represent the type of every expression and sub-expression in your language as you're type checking. In this treatment, we're going to be using the exact same data structure for both of those. However, they don't quite cross over perfectly, even in this very simple implementation. Specifically, this little guy right here, typegen, which is loosely similar to quantification that you would see in Haskell. This is only really going to be used in our inference algorithm. There's not technically a way to express this in a data constructor. But we'll get to what all of this means when we get to the type inference portion of the talk. So let's get right down into parsing. Who here has used Parsec before? Has familiarity? Okay, everybody. Awesome. That's going to make this really easy to get through. So since everybody already knows what Parsec does, you can ignore basically all this and just look at this guy right here, grammar. Grammar is going to be the actual parser objects, or the parser data that we're going to use. It's simply going to take this expression parser, parse as many spaces as you can and then an expression until you get to end of file. So the Parsec library exposes a type called parser A, which is the main interface that you use to express parsers. And the type of a parser A looks very similar to the type of our parse OHML function to start with. It's a data constructor that wraps a function that takes a string and returns either an error or the value of the thing that you're trying to parse, plus some other little details that I'm going to gloss over. And the interesting thing about this is it makes it very easy to take individual small parsers that only parse one thing, like a num, a string, or any other small atomic elements, and combine them together using combinators into larger parsers that have the exact same type representation, which is something I'm sure you're all very used to, programming in Haskell in general. Parsers, or parser type in Parsec is an instance of monad and a bunch of other useful type classes. In this talk, we're going to be using the control.applicative library almost exclusively. These two operators right here are from control.applicative. If you look at this guy right here, it should be pretty obvious what's going on. So this is an operator that takes a type FA, F being parser in this case, and an FB and returns an FB. So literally what we're doing is saying match on all these spaces. If there's an error, propagate it to the right. If not, just return whatever the thing on the right parses. All of the combinators we're going to be using in this portion of the talk are left associative. But before we get into more complicated examples of Parsec, let me show you some other high-level features of what the library allows you to do. It has a couple of tools that can generate tokenizers for you, and also some complicated expression parsers that can be kind of generated from static data. So in this case, we're going to define the keywords in our language and this list of operators. And if you notice, this is a nested list, and they're arranged in precedence order. So times and divided by bind more tightly than plus and minus. If you notice this guy up at the top, this little string here with nothing in it, that's actually function application. So F space as the infix operator X is F applied to X. So this is some jive that's not really necessarily important. If you're interested in seeing how this works, I highly recommend you take a look at the Parsec documentation. This is effectively a recreation of a parameterized module. The idea is you can define some high-level properties of what your language looks like in this record type, language def. You can pass it into this function called makeTokenParser, and it returns you another record with about 40 fields in it that all are parsers for various types of primitives. We're going to use a bunch of them I'll be pointing them out as we go along. Does everybody know what this is? This is a record wildcard syntax. So I'm literally binding every field in this record into scope so I don't actually have to pass a reference to the token parser that comes out of this. So here's some examples of some slightly more complicated parsers. Identifier is a tokenizer from the make tokenizer record that we just generated. This operator right here is just fmap, which I'm sure you all are very familiar with. So here we're literally saying, if you look at this guy, you'll see that its type is actually, yeah. Pay no attention to all these guys. It's type parser string. So if we fmap this sim constructor on top of parser string, we of course get a parser sim. And these guys are doing pretty much the same thing. The only real interesting thing on these pages are these two operators right here. This, which is app, and this guy, which doesn't really have a name. I'll just call him questiony. The interesting thing about this guy is type. It takes an f of a to b, an f of a and an f of b. So what is this really doing here? It's taking this function, applying it to this parser. But what do we actually get here? We actually get a partially applied function wrapped inside of this parser data type. And this magical operator right here allows us to then combine those things from left and right, exactly like function application works. So the interesting thing about this, and the reason that you hear control.applicative and parsec mentioned so frequently together, is because of this kind of natural synergy between function application reading left to right and parsing things left to right and just data constructors being left to right application makes it very easy to compact this all into one expression. And then this guy right here, questiony, just allows you to attach some metadata to your parser that when you actually parse an error, allows Parsec to generate a friendly little error message for your users. So if I take a look at one of these guys, as I mentioned before, because of the combinator-based interface for Parsec, it's actually really, really convenient to just go through your program and test all of these individual parsers as you go. You don't have to build up the whole parser. You don't have to write a complete program in order to test that your parsing works. So parsing this list of possible symbols here, we get a correct func, let with two T's, an F, that thing concat map down at the end, and this nice little error message that says a thing that starts with a capital letter is not a valid identifier. So this is pretty straightforward. The only real things that are introduced here are two additional parsers that came directly out of the make tokenizer call that we made earlier. Values are pretty straightforward, but we're introducing a new operator here, this guy, alternative. What the alternative combinator does is it takes two parsers or two instances of applicative. In this case, the semantics of it is it will try the parser on the left. If the parser on the left fails, if it returns a left, and the continuation, the string of values that it's parsed is the same as its input, it will then try to apply the parser on the right. So in this case, we're saying a val is either a symbol, a literal, or a constructor. We know that in the first character, we can tell the difference between these three. So we can just use this alternative combinator directly. Our language is going to have patterns, as I mentioned before. The only two new things that you can see in here are parens and many. These are two other combinators from Parsec. Parens is just going to take a parser and apply the exact same parser, starting and ending with an opening and closing parenthesis. Many, if you actually look at the type of this guy here, takes an f of a and returns a f of list of a's. So obviously it takes a parser, applies it many times, and returns you a list of all of the values that it parsed. So finally, we get into parsing the actual expressions in themselves. It's a simple alternative case where we're trying these individual parsers for each of the data constructors for the expression type that we saw earlier. You see this guy pure, which is the exact same function in this case as return from the monad type class. We're lifting this function into a parser. We're then rolling it down this list here. We're applying it to the reserved fun. Reserved is a function that takes a string and returns a parser that matches exactly on that string. So in this case, it'll match on the word fun. It won't match on fund or funtastic or tabulous or anything like that. We then map that onto a symbol, the arrow, an expression, and we want to return the error message abstraction if this doesn't match. I think you guys probably get the point. Thought this was just kind of an interesting little thing. If you can cover up this side of these expressions right here, it's actually really easy to see what's going on and why this is called applicative in the first place, right? We're taking a function, we're applying it to its arguments, but it just so happens that the arguments in this case are in some sort of data structure where we need this translation layer in order to properly apply them. The last thing we're going to talk about in Parsec is this function, build expression parser. This is a real neat guy that works very similar to make token parser. It's a thing, it's a function that takes a specification about what we want our parser to look like and returns a very complicated parser that does a lot of the hard work of dealing with left recursion and associativity for us. So the key thing to look at is this guy. The first argument to build expression parser takes this complex data structure that represents a specification for how you should parse expressions. It's very similar to what the ops table looked like earlier on. We have to wrap it in this data constructor that tells us whether it's an infix, prefix, or postfix operation, and also what its associativity is. In this case, everything in this language is going to be left associative. Everything is going to be infix. There's some complexity involved in actually constructing this data structure. And to be entirely honest with y'all, this function was my white whale in writing this talk. I was absolutely obsessed with making sure that this was point-free. And it was probably a bad idea. So try not to pay too much attention to that. Just bear in mind that if you're actually writing a parser like this, you can write these data structures out yourself, and it's not really very hard. And this is a nice little microcosm of everything we've talked about in parsers so far. This is how we parse data constructor strings. This constructor applied to what a type looks like, and then the type itself is exactly like parsing expressions in the rest of our language. We're using the build expression parser and this table. There's only two ways that you can make types, type signatures themselves. There's left associative function application with a space, and right associative arrow application, which is function syntax. In case you're wondering whether or not this actually works, it does. All right. Welcome to type inference. So a couple of things to say about type inference to start with. Type inference is a very complicated subject. This is a very shallow treatment of it. Type inference is also kind of an opinionative thing. There's not one way to do it. Every language does it a little bit differently. So while you're going to see a lot of similarities between these sorts of algorithms in the fields, don't take this as the verbatim way to implement a type inference engine. So the general strategy that we're going to follow here is fourfold. We're going to walk through our expression tree the exact way we had a single function for every type in our AST. We're going to walk through it, and for every symbol that we find, we're going to introduce an assumption. An assumption is just a tuple, the string that represents this symbol, and what we assume the type is. Now, when we actually when we actually get to the symbol, we might not know anything about the type. In that case, we're going to be introducing a type variable for that. You might be asking yourself, well, if we don't know anything about it, we're just introducing a type variable, how does that actually help us infer types? Well, we're not going to stick with that type variable. As we walk through the rest of our program and we see these symbols used, we're going to restrict what that type variable means by introducing substitutions. A substitution is simply a tuple of a type variable and a more specific type. When we want to actually figure out what the type of something that we've already seen is, we're going to take the assumption out of the list. We're going to go through every substitution that we've accumulated so far and apply them one at a time if they apply, and we should get the most current notion of that type up to this point in inference. And then we're going to have two operations. Unify. You'll see where unify is used as we get further into this algorithm, but unify basically says that when we have two notions of what the type of something is, we have to be able to say that they're equivalent. And the way we do that is by trying to calculate the smallest set of substitutions that when applied to both of these types, we end up with the exact same value. And the last thing that we're going to do in this algorithm is a process called generalization. Rather than explain what generalization means right now, I think by the time we'll get to it, it'll make a lot more sense. So the actual strategy that we're going to use comes pretty much from the Typing Haskell and Haskell paper. It involves this data type, type check, which is the state T monad transformer applied to the either error type, which simply means this is going to be a monadic computation. It has some state, a list of all the substitutions that we know of, and this int, which I'll explain in a second. And it can either succeed and return an A or give us an error. We're going to need an ability to introduce fresh type variables. So as we're going through this algorithm and we see new symbols, we're going to want to say, this symbol X has some type. But we don't want to just say that the type is some string that we make up. We have to make sure that it doesn't clash with something else. We have to make sure that the type that we're assuming this thing to be has a unique identity. And the way we're going to do that is with this computation in the type check monad. It's going to get the state and use this integer I to generate a unique string that represents what the type of that is. We're going to need assumptions. As I mentioned before, an assumption is just a tuple. It is a tuple of a string, which is the name of the actual symbol that we're assuming has some type. And this data constructor called a type abstraction. If you're familiar with type theory, a type application like list num or something like that, list in that case works very similarly to the way a function works. List is a function at the type level that takes another type and returns the type list num. And in our system, all of the assumptions are going to be type abstractions, even though they might not actually have any arguments. So you can see here some infix operators from JavaScript that we've defined in this language that we've come up with so far. Minus is a num to num to num. Plus is very similar. And this guy might look a little weird. Equals is a type gen 0 to type gen 0 to bool. And what that means is whenever we see, we'll talk about what this means more when we get to generalization, but the idea is every time that we use equals as an infix operator in our program, we don't want to assume anything specific about that usage of equals in terms of what equals means as a type. If we see equals applied to two numbers, and then later on we see equals applied to something else, we don't want to assume that equals can only be applied to numbers. So what this gives us the ability to do is say every time we say equal, we're going to use this as a function template, basically, to generate an entirely new signature for equals every time it's used, thereby making sure that we keep these symbols general. Yeah, and the process of actually taking these signatures and generalizing them is obviously called generalization. Of course, we're going to need a simple ability to define these assumptions in scope, test, which gives us a really convenient way to check for unbound identifiers in our language. So substitutions are pretty straightforward. As I mentioned, The type substitution is simply a list of type variables bound to types. We have this simple list comprehension for generating extensions to our current notion of substitutions. We're simply taking all of the old substitutions and applying whatever new substitutions to those, and then generating a new list of all of the substitutions we have. And we're going to need this. This is an artifact of the typing Haskell and Haskell paper. We're going to need these two functions, apply, which takes the substitution and something and applies the substitution to it, and getvars, which just gives us all of the type variables in something. What are those things? Types, lists, assumptions, abstractions. If you notice, there's not actually really a lot going on here. A lot of this could probably be replaced with a generic approach. The only real things that are going on here are the application on those top two lines here. And for getvars, this is really the only guy who returns values. Everything else is just telling you how to recursively traverse the various data structures that we're using to represent types. So now we finally get down to the meat of the application. Unification. We'll see how unification works in a couple of minutes when we actually start type checking some of the values from our expression type. But basically, the unification step takes two types and tries to calculate a set of substitutions called the most general unifier. Most general unifier is the smallest set of substitutions that, when applied to both of those types, yields the exact same values. And calculating most general unifier for our type system is actually going to be very straightforward. If you take two types and they're both type applications, then all you have to do is unify the things that you're applying, and then unify the values. If you're trying to unify two type symbols and they're the same string, you win. You don't have to do anything. It's free. If one of the symbols that you're trying to unify is variable and the other one is anything else, then all you have to do is introduce a substitution that says this variable can be replaced with this type. Anything else is a type error. And the only really interesting thing to come out of this is this guy. How many people have been bitten by an occurs check in Haskell before? Everybody, awesome. How many people actually know what that means? Everybody again. Okay, cool. I can't count very well. Well, I'm going to explain it to you anyway. An occurs check is very simply means almost exactly what it says. It checks to see that when you're binding a variable to some type, when you're introducing a substitution that says you can replace this variable with this type, you want to make sure that this type doesn't have this variable in it. If you have the type A, the type variable A, and you want to say it can be replaced with the type list A, well then, if you keep applying that substitution, you're going to end up with list, 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 list out into infinity. And that's obviously, I mean, you can't actually construct values in finite machines that have infinite types. To demonstrate that, I've written this small program which is trying to construct an infinite type right here by deconstructing this cons pattern and trying to reapply it with the tail of the list. So it's saying occurs check failed. The type symbol that I'm trying to introduce on the right side of that match fails the occurs check. The last piece that we're going to talk about is generalization in type check. Generalization is actually a very simple concept, but there's a little bit of an art form to figuring out in your language exactly where you want to apply it. You don't want to apply it to every single binding that you find because your program will be too general. You don't want to apply it nowhere because your language will be completely unusable. In this language, we're only going to be applying it at let bindings. So right here. The basic practice is we're going to take whatever's on the right side of this let binding. We're going to get all of the free type variables in that expression, all of the type variables that weren't introduced here, and we're going to generalize them. We're going to replace them with this template value, this type gen value. And that way, whenever we see f, Like here we're applying f to 1 and 1. Here we're applying it to strings. And typically if we were walking through this thing and introducing substitutions for f, well, we would see f applied to 1 here, and we would say, oh, well, f has to be a function that takes a num and returns a num. And then we would see f applied to a string, and we'd say, that's a type error. I just read that f was applied to nums. Now I'm seeing it applied to strings. But because it's generalized right here through this let binding, we're going to be able to use it as many times as we want on as many values as we want. And the actual practice of generalizing is fairly simple. We're going to take a list of type variables and a type, and we're going to replace all of those type variables with type gens. So this is the actual just taking that very simple algorithm and lifting it into our stateful type check monad. And this is the, we're saying we want all of the type variables that are in this expression without the type variables that are in the, or I'm sorry, all of the type variables that are in existence without the ones that came from the environment. We only want the ones that were actually in the expression. Of course, the opposite of generalization is we're going to want to be able to instantiate these type abstractions. We're going to want to be able to take an abstraction, and every time we see it, we're going to want to generate a fresh type for it by replacing all of those type gens with concrete type variables that are new. So finally, we get down to actually inferring types. We're going to have one of these functions for every type that we introduced in the AST portion of the talk. Unfortunately, this slide uses absolutely none of the machinery that we just spent 15 minutes explaining. But that's all right, because we'll get to it very quickly. Interestingly, when type checking a pattern, you can't just return a type. A pattern can bind to a symbol, which means it can introduce an assumption. So when you're type checking a pattern, we actually have to return a list of all of the possible assumptions that were created when we were walking through it. So for a literal pattern, we can just return the type of the actual literal. For a symbol pattern, we have to introduce a new type variable to represent the symbol. And then we can say the type of this thing is that new type variable that we introduced. And we're introducing this assumption that says that symbol is of this type. Notice that we're just creating a type abstraction directly from this type here. We're not actually generalizing it. When we get to an actual a constructor or data constructor, we're going to have to, we already know something about that data constructor. We're not introducing something new. This is a symbol that we already have some type information about. So we're going to look it up in the list of assumptions. We're going to get back a type abstraction. We're going to instantiate it with the instantiation machinery that we wrote earlier. And we're going to return the type of that instantiation. When we get to an actual data constructor with arguments, it gets a little more complicated. We're going to do the same thing that we did before. We're going to look up that constructor. But then we actually have to apply pattern checking to all of its possible arguments. And then, once we have the types of all of its arguments, we're going to finally pop out our unify. We're going to have to say that the notion of what this, the type of this constructor is in our list of assumptions is the same thing as this type that we construct by simply listing out all of the types of our arguments and this made-up type that represents what the application of this data constructor should return. So finally, we get down to actually type checking our application itself. Literals are still very easy. That hasn't changed. What has changed is everything else. When we get to actual variables or constructors, we can simply look them up and make fresh instantiations of them. If you look up the way that Hindley Milner works in Wikipedia, you're going to see a lot of equations that look like this. I'm not actually going to go over what these mean, but I thought I would supply them alongside with the actual implementations in our type check monad, just so you would kind of get an idea that this isn't all theoretical, made-up mumbo-jumbo. It actually has a direct application. In this sort of syntax, what you see is a set of premises on the top and a conclusion on the bottom. This is called a judgment. X in this case is a symbol. Colon is an assumption. This little, I think this is a sigma, is that correct? Lowercase sigma represents in a theoretical treatment, it's called a scheme. We're calling it a type abstraction. This little tau, this little lowercase tau here is a type, gamma. This uppercase gamma represents a type environment. In this case, we're hiding the details of this in our type check monad. No idea? Turnstile. Turnstile represents insertion. In this type environment, you can assert this thing on the right. And horizontal line represents judgment. So when we get down to let expressions, we see our first and only application of the generalized function that we talked about earlier. We're going to introduce a new type variable for the symbol that we're binding, this guy, x. We're going to check this guy, the value that we're binding x to, in the environment where we assume that sim is some type that we just made up. This part right here is the part that allows us to recursively reference x within this binding. And then once we have that notion, we're going to have to unify our notion of this type variable that we introduced and the actual inferred type that we get out of this value over here. And once we have that information, we can introduce that assumption into scope and type check the rest of the expression. Application checking is very simple. We simply have to check that the individual parameters line up. This is very simple, similar to our data constructor checking that we saw earlier. We're simply recreating this type, the return type and the argument type, and matching it against the type of the function that we looked up from our list of assumptions. Abstraction is quite easy. Some languages, the variables introduced in an abstraction or in a function, this guy, are generalized. In our case, they're not. You're not going to be able to use these variables polymorphically in this language for various reasons I'm not going to go into. You might think that, that pattern matching is just kind of a degenerate case of abstraction and application. It turns out it is when you're generating code, but not when you're type checking it. In general, you can kind of ignore all of this noise and just note that we're doing the exact same algorithm that we were doing earlier when we were checking patterns. But once we have the type of a specific case, we then need to take whatever additional type information that we learned from that case and unify it down the list of cases to make sure that if we assume in one case that the expression we're matching on is an int, in some other case we don't want to assume it's a string. And then we have this little degenerate case here, which is really simple. When we see a user data constructor, we're going to do these two little checks here, check valid and check mono. And then we're just going to go right ahead and introduce exactly what that type abstraction is directly into scope with no other cupola. But you might want to know what those things are actually doing. Check valid is simply making sure that our data constructors we're not expressing a GADT. We're making sure that if it's just a type, we're fine. If it's a type application, we want to make sure that the thing on the far left of the type application is a concrete type and everything else is a type variable. We also want to verify that every type variable in the signatures that we declare for user-created data constructors are monotypes. We want to make sure that we're not applying a type variable to another type variable anywhere. Once we've done that, we should be able to type check our application. Surprisingly, yeah, it did.
Well, yeah, just that was the number and the string didn't line up.
Right. There are a bunch of errors, explicit errors in our sequence of sample programs at the beginning. At the end of the talk, you can actually see that I'm not making this up.
So that was correct?
Yes, that was correct. Well, I mean, you're going to have to tell me at the end, but I think that was correct. Pretty much, yes. So finally, we get to the last portion of the talk, code generation. Code generation in this language, we're going to be compiling to JavaScript, and we're going to be doing it using the JMacro library. In this case, JMacro is a library for interfacing with JavaScript, generating JavaScript in Haskell. It has a very useful quasi-quotation interface. Everybody in here knows what quasi-quotation is in the context of Haskell? No, yes? Probably. If you don't know what it is, don't worry, because we're going to introduce it in the next slide. Or maybe not. So a couple of the things that JMacro gives us for free, if you take a look at other treatments like write yourself a scheme in 24 or in 48 hours, that's a treatment that is an interpreter. It's actually like calculating the values of the different programs that you feed it. We're not going to do any of that hard stuff. We're just going to generate JavaScript code and then run it in Node.js. And JMacro does a lot of the heavy lifting for us. We don't have to come up with our own AST for JavaScript. JMacro has one. Turns out JavaScript is very complicated, so it's lucky that we didn't have to do that because we would run out of time. It has a nice render for that AST. You can just pass it in, and it'll generate nicely formatted JavaScript for us. As a quasi-quoted interface, which we're going to show in a second, but what it basically allows you to do is write statically typed JavaScript directly in your Haskell and do some other really interesting things. It also has, it's hygienic. In the variables that you introduce in your JMacro snippets, if you say var x, when it actually renders into JavaScript, you don't end up with the literal symbol x. It's going to take that x and it's going to generate a clean name for it that's guaranteed not to shadow some other x that might be in your application.
Not the same.
Not the same. So we saw this guy earlier, generate.js. It's going to call this function toJExpression, which is going to take some type that's an instance of the toJExpression type class and turn it into a JExpression data type. We're going to take our entire AST and make it an instance of the toJExpression class. But before we get there, here's a little introduction into what a quasi-quoter looks like. So we have this function console log x, and then this weird syntax, and then suddenly the syntax for our comments changes. It is no longer what you're used to in Haskell. And suddenly we're writing things that look a lot like JavaScript. And suddenly, in the middle of our JavaScript, we are referencing variables that were declared in Haskell. I thought so too, but it's actually not. I know, it's crazy. But before we get to exactly how that works, there's some very simple things we can do. To make an instance of the toJExpression class for our literal values, all we have to do is unwrap the data constructor and call toJExpression again. We already have instances for virtually every simple data type that you might need to use. But the quasi-quoted interface doesn't quite give us everything we want. So for a couple of places in the rest of the talk, you're going to see some places like this where I'm manually constructing pieces of the JavaScript AST. Specifically, I didn't want to deal with tracking like how our variable names map to the variable names that we're rendering. I just wanted to use whatever variable name you use in the language should be exactly what shows up in your JavaScript. So in this case, I'm using this ref function to manually create a JavaScript AST symbol named exactly what we want. And if you look at this guy right here, you can see that within this block, I'm anti-quoting back into Haskell, and I'm calling this ref function on the string test. And I literally end up with a data constructor, valExpress, jvar, string identifier, test, which is datum that represents a symbol in JavaScript. So here's a more complicated example of using JMacro. It's going to be useful in our language to introduce new symbols into scope. Because our language is an expression language and everything is an expression, at the time it kind of made sense to just make everything render to an expression. But because of that, obviously these three statements separated by semicolons are not a valid expression, so you're going to see a lot of things wrapped in functions. An interesting thing to note here is we're declaring a function in JavaScript, and I don't know if I mentioned this yet, but everything between these two brackets looks like JavaScript, but what's really happening is this entire string internal part is being passed to the quasiquotation interface. It's parsing it as a string, and it's returning a representation of the Haskell AST, and it's being inlined directly into our code. So while this looks like JavaScript, it's actually just a bunch of composed data constructors that represent a JavaScript AST strung together with some magic from the quasiquotation interface. This terminology right here allows us to anti-quote. So since this is being generated directly into Haskell, there's no reason why we can't put Haskell right back in the middle of it. In this case, we want to be able to return the rendering of the expression, right? So all we have to do is just anti-quote and put the expression. We're going to write a 2J expression instance for our expression data type later on, and that's going to allow Haskell to just, the quasiquotation to just render JavaScript AST directly from that.
You have to go back and keep track of something defined above.
No, but I mean,
Now
in some treatments you would, in this one you don't.
Okay.
The only other thing to note about this particular function is this interesting thing. You saw earlier I was defining a variable in Haskell and then using it inside the quasi-quoted block. At this point, it should be fairly obvious what's going on there, right? If this just compiles down to Haskell, then there's no reason why you can't just reference Haskell variables directly in your JavaScript. But there's something even weirder going on here. I'm declaring a variable in JavaScript and then using it in Haskell. Well, it's interesting. As I mentioned, JMacro allows you to declare hygienic variable names. But because of that, if you're going to nest calls to JMacro, you don't actually know what the name of this thing is later on. Arg right here isn't going to be called arg inside this expansion. So in order to know what this thing gets generated as, I pass it in here. Now, arg here isn't a JavaScript variable, obviously. Arg is exactly what you think it is. It's an AST node that represents a symbol in JavaScript. So you can see here, obviously, f is type J expression to some value. It's not taking like an int or something. It's actually just taking an AST node. So now we finally get down to actually generating the code for our language. Variables are very simple. Abstractions or functions are going to use the intro machinery that we saw earlier. We're going to introduce a symbol with this modifier function that allows us to just kind of generify how intro works. And we're going to want to say that this symbol should be bound to this expression. And this little guy, there's a lot of parentheses here, but it's really simple what's going on here, right? We're rendering whatever f is, and we're applying it to whatever x is. As I mentioned earlier, you can, at least in the code generation part, you can treat lets just like applying a function to a value. It's just an abstraction and an application rolled into one. And that's literally what we're doing right here. We're introducing a symbol that should just return whatever the binding is, and then evaluating the body of the expression inside that introduction function block. But this is where everything basically starts to go off the rails. Unfortunately, if I had another 3 or 4 hours, we could do a much more we can do a much better coverage of exactly how to do a proper optimized implementation of rendering things to JavaScript. In this case, since we decided to just say everything's going to be an expression. Unfortunately, we have to shoehorn some things into expressions that don't quite fit. In this case, when we want to introduce a data expression, we have to come up with some sort of function and scope that we can use as this data constructor wherever we see it apply. If we define cons as a data constructor, we need to have a function and scope called cons. That is curried. It's got to be a function that returns some value that represents a con cell. But it could also potentially be a value, right? Nil doesn't take any arguments, and we want to be able to say that a nil matches any other nil. So there's a lot of weird cases going on. If you see here, when you introduce a data expression, I'm saying that the symbol scheme is some application of this curried fun function. I think you can probably figure out what curried fun does. It takes the data about our type expression and generates recursively a series of nested functions that eventually return some value that represents whatever applying that data constructor to a bunch of arguments should return. Match expressions are once again very complicated. Again, this basically comes down to if you were actually writing a real language, you wouldn't bother trying to shoehorn everything into expression. But in this case, when we have an actual match, we have to break it up. The only thing we're introducing here is this data constructor called match, and all that really does is create a tuple that has a specific type identity. The tuple is the value that we're matching and the pattern that we're matching it to, and this variable scope. The reason that scope exists is because within this match, we're going to want to introduce values. But because the matches themselves are expressions, that means this thing has to be a function. Because that thing has to be a function, it introduces its own scope, which means if inside of here I say var x equals 1, it's going to disappear as soon as it gets into this body. So instead of doing that, I introduce this variable scope. I bind it to the scope of the match expression itself, and then thread it into the rendering of the actual match. We're almost there, folks. Curried fun uses pretty much the exact same strategy. We're creating this array at the top level for things that are functions. This is view pattern syntax. Because we have kind of a largish expression, I kind of condensed down some of those composite data constructors into this view pattern. This just returns, if it's a function, it returns the function in the argument. And we're saying, if the data constructor is a function, you should create one function. When you invoke the very first function, you should create this array that's going to accumulate the arguments, and then you recursively walk down curried fun prime, generating all of the individual argument captures. If it's a value, like nil, you just want to render the object directly, because it's not going to take any arguments. You don't need this. And we certainly don't want to actually invoke a new constructor for nil every time we see it. So this is just the recursive application of what we saw before, partially applying each value of the data constructor and pushing it onto this args list. And when we finally get to the bottom, this is what a value that results from one of our data constructors actually looks like. An attributes property that just has our accumulated arg list on it, and this type property that represents, it's just a string that is the name of the data constructor itself. We use this because I couldn't figure out a good way to use the instance of operator in the quasiquoter. And finally, we see matches. So this is the actual binding of a value itself to a pattern, right? This is the thing that actually goes inside of our conditional, inside the if. If we're binding a value to a literal, we just want to see if the literal is the same thing as the value. But it gets a little more complicated when we're introducing symbols. When we're introducing symbols, we want to take that scope accumulator that we were passing down and set the symbol's name in scope to be the value, and this should always succeed. So we're going to return true. When we match on an actual constructor, because we can't use instance of, we're going to check to see if this type field actually matches the name of the constructor that we're passing in. Wow. I'm not even clear I should bother with this. But basically, when you're iterating over an application of a constructor pattern to a list of symbols, you have to take everything we've learned about JMacro so far and roll it into one function. We're going to have to check to see if the type of the constructor matches. And then, because we could have further matches in the arguments list that don't work, we're going to have to say, and the evaluation of this body, where we iterate over all of the arguments, apply the exact same match algorithm to each one of the arguments, which, of course, might introduce new bindings themselves, and then return the accumulated conditional that says whether or not every one of those patterns matched. And of course, that just looks like this. We're just left folding ands over that series of pattern matches. So if I played my cards right, 2 plus 2 equals 4 is true. 4 plus the string whoops is a type error. If we let x equal 1 in the expression x plus 1 equals 2, that's true. This isn't a valid expression. Applying the function x plus 4 to 2 is equal to 6. That's true. That's the 13th, that's the 7th Fibonacci number. There's some other stuff in here. Node.js takes kind of a long time to start up, so I'll just let that guy go in the background. That's how you write an ML compiler in Haskell with Parsec and JMacro. Any questions? Seriously, though, any questions? Any questions at all? Oh, thank you.
You have a larger project, and then this is the distillation of what you did in your larger project?
I didn't plant this guy, by the way. He's actually asking about forml legitimately. Yeah, so forml is a language that I wrote to kind of explore some of these concepts. I was interested in learning how programming languages work, and Gershon was showing me JMacro. It looked really interesting. It looked really easy. It turned out to be really hard. But it's an interesting language. I mean, it looks very similar to a lot of the stuff we did earlier, but it's got some other stuff in it. Tail call. We skipped optimization entirely in this. Obviously, the language that we just wrote is horribly malperformant. It does do all the things that were advertised. Not blowing the stack is not one of those things. Optimization itself is a very detailed subject, obviously. There's a lot going on in there. There's some other stuff. It tests things. It's got this nice kind of inline testing feature. If you've used, this is a testing library from JavaScript called Jasmine. So the language actually allows you to kind of write assertions inline that compile to their own test suite. Some other stuff. It's an interesting project. It's about 5 orders of magnitude bigger than what we just saw right here. But if you're interested in the subject, you might want to take a look at it. Thanks for asking.
And for what it's worth, if you ask him, he'll present what I found to be a fairly compelling argument for why you should use forml instead of fey.
Those aren't fighting words, but they're nonetheless true. Anybody else? All good? Jay?
So presumably then in formal you're not trying to force everything into just being functions and so on. You're using more of JavaScript as your back end?
It depends on what you mean by more. Formal is like ClojureScript. It's designed to target Clojure advanced mode. It leverages Clojure. Is everybody familiar with Clojure tools from Google? It's a JavaScript to JavaScript optimizing compiler. It does a couple of things very well that Formal leverages pretty heavily. One of them is function inlining. A function applied to an argument under most conditions will just be directly inlined, which is real nice. And it ends up making code that, well, I'm sorry, I can't actually show you any of the code without wasting a ton of time, but I mean, the entire prelude is probably about 1,500 lines of formal, and it compiles down to about 11K of JavaScript, so it's, advanced mode is real efficient at doing that.
But the JavaScript is not supposed to be for human consumption?
Absolutely not.
Right, okay.
I mean, ideally, I hear ASM.js is the new hotness. It would be nice to compile to something. I mean, formal, I don't, you know, I don't want to go decision tree, total decision tree or anything, and just explain all the advantages and disadvantages. In brief, formal is designed from the ground up to be fast. It has extremely aggressive function inlining everywhere, even functions that you define in the language, tail call optimization, dead code elimination, a bunch of other features that just basically make it perform in a way where you don't have to get bitten by the functional programming bug. But definitely not human readable. Not even really programmer readable.
I heard
I'm not
Faye
sure if I
mention.
can answer your question. I'm sorry, but go ahead and ask it anyway.
What's formal for?
It's for programming things.
No, that's a good question. That's
Well, no,
basically
it is a good question. Let me give you an example of what formal is good for. Yeah.
Is what? What is it?
Well, one thing you can do is
That's another language.
you can play Tetris.
So where does the compiler live? It lives
The
at
compiler is written in Haskell, and it uses a very similar architecture to the architecture that you don't have to see this anymore.
Use the compiler and you produce a bunch of JavaScript and then you ship it into your browser from far away.
Yeah, you can ship it in a browser. You can ship it in Node.js, runs in Node, Phantom browsers, everything back to IE7.
It's for people who are prejudiced against JavaScript but sort of dream of doing Haskell.
It's for people who like to use languages that aren't finished.
Right.
I don't know who said that, but that was funny. Yeah. That's good. Hypothetically finished is what I meant.
Does formal have any kind of bindings or FFI to JavaScript code, or is there a plan to implement
I love
that?
all these formal questions, by the way. Yes, actually it does. So a lot like if you're familiar with Ruby. What did I, fuck. How did I go back? Well, if you're familiar with Ruby, it has a very similar native, kind of like an FFI. So let me see if I can find an example in here. So these little backticks right here are quoting directly into JavaScript. A little known fact is it's actually quoting directly into JMacro, which has its own syntax sugar that I didn't talk about in this course, or this talk. But JMacro syntax sugar is almost a language in and of itself. So there's a lot of stuff you can do with this. But I mean, as you're all familiar with Haskell, I mean, the interesting thing to notice here is this do is introducing a do block exactly like it would introduce a do block in Haskell. Anything that's quoted in backticks is basically just a type IO whatever where you can't actually infer what the generic argument is. So this is just the monadic bind without an operator saying do this and then do that. And they are actually functions, but when this gets compiled, the functions get compiled out and it just turns into a semicolon in the optimization step. It's pure-ish. The semantics of the language don't allow you to do any side effects, but because you have unrestricted JavaScript, it does return a box type. Like when you bind something to quoting directly into JavaScript, it doesn't execute. But then you can, wherever you want, you can use a do with this little exclamation point right here, and it'll evaluate it immediately. So the idea is if you want to write programs where you're tracking side effects through the type system, you can. If you want to stick a log in the middle of your pure function, you can do that too. And it basically falls on you to make sure that you're using the type system as a tool and not a millstone. All right. Thank you all very much.